Sample exam 5, number what, 18? Okay, number 18 we have a integral from e, it says, to e squared of 1 over x ln x dx. So ultimately our issue here is solving this definite integral. It's not a known derivative, but hopefully we recognize that a substitution of ln x would be good here because the du would be the other part, 1 over x dx. Which ultimately, if we replace the ln x with u, we'd have 1 over u. The 1 over x dx part would just simply be du. And so we'd have that, and scratch the, sorry, make blanks on there, remember, because we changed the variable to u instead of x. So ultimately, if we substitute properly, again, the ln x is replaced by the u, the 1 over x dx part is replaced by du, and then from there we can anti-differentiate. We get natural log of absolute value of u, and then plug in our ln x again. And we can put in our e squared and our e. And we do that, we'll get ln of absolute value of ln of e squared minus ln of the absolute value of e. And ultimately, these two right here make 2, so we'd get ln 2 out of that one. These two would make 1. Ln of 1 we know is 0, so ultimately we get ln 2. And looks like that should be letter A. Ultimately, it's an AB problem because it's just using U substitution. Others? 15 through 20? Jake? 15? 15 like 5 or 6? 15. Okay, on 15 we got a table here. And in that given table, we have some values for x and some values for f. And it says on this closed interval, using the intervals 1 to 3, 3 to 7, 7 to 8, and so on, what is the approximation for the area under the curve obtained from a right Riemann sum? So ultimately, again, keep in mind that we're, if we were to draw these points here, we did 1, negative 2, we have one that's below. We have 3, 0 right there. We have 7, 3. And we have 8, 3. And we have 10, negative 4. So ultimately our curve, maybe has some shape like this, whatever it may look like. Okay. All right, and ultimately if we use a right Riemann sum here, keep in mind that when we use a right Riemann sum, whether the curve is above or below the x-axis, okay, we need to go from the x-axis to the point in question at the right end point, which is down here to negative 4, and then we need to draw left to the next point in question, which again 8 to 10 is our first interval, and so therefore our rectangle would be as such. Alright, and again, remember, all we're doing is we're drawing a rectangle that has one of its dimensions on the x-axis. The other one, okay, goes to the height of the point in question at the right end point. And then we'll do the same thing from this point over to its interval, which ultimately would be something like that. Because it's above in this time, and this one is above, so we'd go over like that. And then for the last one, it would just be degenerate because the height here at the last one would be 0. Remember, with the right Riemann sum, we don't use the left endpoint at all in terms of finding a height for a rectangle. And so ultimately, those would be my 4 rectangles. Again, one's height would be 0 because it's measured at 3, 0. Okay. These two would be measured above the x-axis because they're both positive valued at the right end point of each of those intervals. And this one at the end of the right end of this interval is a negative value. So with that, if we calculate the areas of these rectangles, we'd have 1, 2, 3, 4, 4 by 3. So ultimately that one right there would be 12. This one's 1 by 3, which would be 3. This one's 2 by 4, which would be 8, but negative. So with that said, we'd have 15 plus negative 8. Should be 7. And ultimately that would be A-B problem 2, just a Riemann sum application. And again, keep in mind the key issue here is that we start at the right endpoint, and wherever that curve is at the right endpoint, whether it's above or below the x-axis, we're going to draw a rectangle to the point that is to the y value of whatever x in question we have at the right endpoint. So therefore, in this case, we ended up with a rectangle that was below the x-axis, 2 that were above, and 1 that had a height of 0 because it was measured from 3, 0, the right end of this particular interval. What else? Up through number 20. Yeah. Let's see. 19. We got some more values given. And it tells us that f is differentiable on the closed interval 0 to 1. And we have a function g of x, which is equal to f of 3 of x. And the table below gives the values of the derivative. And we want to know what is the derivative of g at point 1. Alright, well in general we've got to recognize that g is defined as a composition of functions, so if we want to find the derivative of g, we're going to need to use the chain rule. And ultimately the outside function is f, the inside function is 3x, so therefore we'll do the derivative of the outside evaluated at the inside times the derivative of the inside, which would ultimately be in this case 3. So we find the derivative using the chain rule, and we want g of 0.1. That means we need f prime at 3 times 0.1 times 3. So ultimately, f prime at 0.3 then. And ultimately we got that answer is in our table. If we look at x is 0.3, f prime is 1.096. And so therefore we get 3 times 1.096, which ultimately would be 3.96, 1.92, 2.88. So it would be letter E. Point 3.288, which would correspond to letter E. And so ultimately that'd be AB also, chain rule. Questions on any steps on that one? Others? Huh? And 20, we have which of the following integrals gives the total area of the region shared by both the polar curves of 2 cosine theta and 2 sine theta. So we got r equals 2 cosine theta, and we got r equals 2 sine theta. So ultimately these are our two curves in question. And we want to know again ultimately what which of the following integrals gives the total area of the region shared by the polar curves. In other words, these have some overlap. Okay, so there's an area that is going to be shaded here. And ultimately, if we were to develop, it might be handy for us to develop a picture of what these might look like here. If you remember, ultimately these are, if I have r equals 2 cosine theta, if I were to multiply both sides by r, I'd have r squared equals 2r cosine theta, which ultimately would give me x squared plus y squared here, and this would give me 2x here. So I get x squared minus 2x plus 1 if I completed the square. And 1 over here, so it's going to be x minus 1 squared plus y squared equals 1. So if you didn't remember what shape that was, you could change it to polar form, or rectangular form, it's already in polar form, and recognize that it's just a circle that's translated 1 to the right. Or you could make a theta r chart and put some thetas in there and develop a graph of it in polar form also, but ultimately we're just going to be 1 here, and 1 here, and 1 here, and 1 here. So we'd have that as our first one. And if we did the same thing with the our sine theta equation, we would end up with x squared plus y squared equals 2y. So we'd end up with x squared plus y minus 1 all squared equals 1. And with that, you can see that it's going to be a translation of 1 up. So ultimately you'd have this, this, and this, and so therefore our overlapping space would be that region right there. Alright, so knowing that, if we are going to find the area of that region, what we want to do, remember, is our formula in polar in general is going to be 1/2 times r squared d theta from some theta to some theta. And so ultimately the our question then, I guess, is what's going to be our r squared, I guess, first of all, if we're looking for an overlap between two curves. We want the overlap between these two curves. Keeping in mind again, this one is the 2 cosine theta 1, and this one is the 2 sine theta 1. If I'm going to integrate, if you will, from the positive x-axis, it would seem like we would have this one right here being the outside function, if you will, and this one being the inside function, keeping in mind that things are measured from the positive x. So let's try that and see how that works for us. So just like our problems when we have rectangular coordinates, we want to make sure that we square first and then subtract second. Alright, so let's check that out and see how that goes here. And then ultimately the next question is, how about the what about the upper and lower limits here? With our upper and lower limits, we need to ultimately figure out when are these two overlapped. Well, remember when ultimately when the calculator is drawing these, if you were to have the calculator draw it, we would start out here at I guess we'll start with this one, with the cosine 1. If we put in cosine of 0, we'd ultimately get 1 here, which would give us 2. So this would be our starting value if we started at theta equals 0. And then it would draw around this way. It's going to be the same thing here as well. With 2 sine theta, actually with 2 sine theta, it's going to give me 0, 0. It's going to start at the origin. Okay. So I'm drawing the one that's on the outside, if you will. It's going to go from 0 to this point. The question is, what would this point be right here? If I got to this point, this would be when sine is equal to pi over 2. True? If sine was pi over 2 here, that would give me, no, I lied. I want that to be, actually, I want that to be pi over, I want that value to be 1, 1, 1. I want it to be equal to y value 1, so actually that would be pi over 6, wouldn't it? I think how those two share 2 cosine, 2 sine. Overlap part. I might have to take a closer look at that one. So ultimately, if we squared, I have a square on that one. Squared these. Make sure I got the picture right. notice that I kept my window at 0 to 2 pi. I see, okay. I kept my window at 0 to 2 pi, and you notice that it went around twice. So if it goes around twice, that means that ultimately it's drawing two different cycles. Okay. All right. And we could also look at if we look at our table. If I can set my table up right. Remember how I had that? Let's see if we start at 0 and we go by pi over 6. Actually, let's go by pi over 4. See what those values are like. So, ultimately, when theta is equal to 0, the two are not together, as we can see. They do equal each other at pi over 4, you'll notice. Okay. And then they equal each other again at, this would be 5 pi over 4. Right. We can go, if they go from 0 to pi over 4, let's say we do that. I think if we can get that doubled. Yeah, I'm going to think about that integrand too. Let me put some thought into this one because I'm going to show you because ultimately the interval they used here, if they used 0 to pi over 4, in general when we've done this in the past, they're generally equal at pi over 4. So we have the actual overlap point. But these don't equal there because they manipulated this so that they just had one smaller interval and then doubled it. Okay. And let me toy around with it a little bit and I'll come up with a better way to be able to do that in a quicker manner than this. All right, so we'll come back to that one later. But let's go. Anything else up through 20? Next part, 21, 25. Okay. 21, we have a limit. As h approaches 0, we got 2x plus h squared minus 5x plus h cubed, which that's to the 5th, isn't it? Minus 2x to the 5th plus 5x cubed all over h. So ultimately we just need to recognize that this is just the derivative of some function. Okay. And what do we put into the function? Here's our x plus h and here's our x. Okay. So ultimately isn't this the derivative of the function 2x to the 5th minus 5x cubed? Keep in mind, why is this a positive now? Because in general, shouldn't this be in parentheses, this part? And if we minus a minus, it's going to be plus. Well, if we were to write it in general, it'd be f of x plus h minus f of x, right? And if our f of x was a quantity like this, wouldn't we have fifth and then third here? Wouldn't it have to be in there like that? It's not what now?
It just doesn't, as it appears on the paper, it's not written like that.
Well, like I said, you can recognize that these two are both 2 something to the 5th, 5 something to the 3rd, 2 something to the 5th, 5 something to the 3rd. Like I said, the only issue is this part, but remember when we subtract this quantity, okay, it would have been in parentheses, and therefore that would be minus and that one would become a plus. Okay. As long as this function and this function are the same, which they are, they're both this. Like I said, if I told you to do the limit definition right now on this, you'd put in x plus h here and x plus h here, and then you go minus 2x cubed minus 5x cubed in parentheses, and then change your minus to a plus, and then you'd have that plus right there. So ultimately we want the derivative of this, so it would be 10x to the 4th minus 15x squared, which would be letter D. So ultimately that would be a B problem, definition of derivative. What else? Through 25. x cubed plus ax squared plus bx minus 8. And it says that here that we have an inflection point at 2, 0, and the question is what would be the value of b. So if there's an inflection point, we know that we have to do something with the second derivative here, so if we differentiate, and then we differentiate again, we have that. Alright. So, ultimately, if we did the second derivative, we'll notice that that there is no b value here, but that may or may not matter. Bottom line is we know, Ian, we got the door. We know that the second derivative equals 0 when x is 2, because they told us this occurs at 2a. So if we plug in our 2 and our 0 for the second derivative, we would wind up with negative 6 equals a. Alright, so at this point our equation is now y equals x cubed minus 6x squared plus bx minus 8. So the question is, that's fine, but still haven't found b. So how do we find b? Is the question. Any ideas? Well, we did plug in a already. That's right here.
I got the door.
So we determined a by finding the second derivative and setting it equal to 0 at that point 2, 0. The key information is at that point 2, 0. This point, this curve goes through 2, 0, doesn't it? So ultimately, if I put in 0 and I put in 2 for x, wouldn't the only variable be b? So we know not only does it go through 2, 0, which says something about the function, okay, we also know it has an inflection point, which says something about the second derivative. So if we do the math here, we're going to get 8 minus 24 plus 2b minus 8. And if we add 24 to both sides, we're going to get 2b over here, so 12 would be our b. 8s would cancel out, of course. And with that, get what number am I here? 23. Be letter D. So ultimately, it'd just be AB. So application of derivative. What else up to 25? Last part, 26 to 28. Matt? Let's see, in 26 we have series x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. So the given series looks like that. And the question here is what are the values of x for which this series converges? Okay. Right. So with our x values here, we hopefully recognize here that we can that the x part here needs to be less than or equal to 1 here in order for this to have convergent values here. If our x was bigger than 1, the numbers would grow, if you will. And so the only way that would happen is if we were absolute value of x less than 1. So if we do that, we'll notice that that is an option. However, one thing that has to be considered also is the endpoints. So let's take a look. If we were to put the endpoints in here, if we put the endpoints into our general form here, which would use this, we'd have negative 1 to the n plus 1. And we'd have negative 1 to the n over n. And so the issue is, does that converge or diverge? If I had negative 1 to the n plus 1, times negative 1 to the n. Well, keep in mind that depending on what these n's were, let's just say for argument's sake this was 3 and this was 4, then that would make this 1 and that negative 1, wouldn't it? And therefore, ultimately, wouldn't the end result be just simply negative 1 over n? Alright, so ultimately if I let n approach infinity here, for this particular sequence, the question is it going to converge or diverge? And if it's going to converge, why? And if it's not, why not? So keep in mind that if we let n get bigger, this is going to be, these are always going to be one bigger than one another. So one's going to have a negative power, one's going to have a positive power, or even power, odd power, I should say. Which means one's going to be 1, one's going to be negative 1. So if we multiply those tops, no matter what those powers are, we're going to get negative 1 over n. Okay? Alright? And so if we let that happen, again, keep in mind the elements that we're going to get here are going to be negative 1, negative 1/2, negative 1/3, negative 1/4, and so on. So the question is, are those going to converge or diverge? What if it was just 1 over n? Converge or diverge? Isn't 1 over n a special case in the p series? So, and what do we know about p? P less than or equal to 1, it's going to what? It's going to diverge, isn't it? So if it diverges, then keeping in mind what could be said about the negative version of that. If it were negative, again, keep in mind it's not alternating, it's negative. Okay. So therefore, would it also converge? The summation is like an integral. Can we factor out the negative and see that it diverges and then multiply the negative back in, if you will? Sure. All right. So, therefore, essentially, because it's p series, right, we could say that it doesn't converge there, and therefore we leave that one alone on the left-hand side. Now, if we put a 1 in there, on the other hand, which I'll do over here, we're going to get negative 1 to the n plus 1, and then 1 over n, because ultimately, no matter what I raise the 1 to, it's going to just be that. Now, what kind of series does that make it if this is still here? Now it's alternating. True. And if you look at the 1 over n, does it pass the alternating series test? Do the elements get closer to 0? 1 over 1, 1 over 1, 1 over 2, 1 over 3, 1 over 4. And since it's alternating, okay, it does converge this time. So therefore, what's our final answer then? Okay, so because this is alternating, ultimately it passes the alternating series test. Okay. This does not. It diverges. Because it's p series. And p is less than or equal to 1. So therefore we would take 1 would be convergent, negative 1 would not. And so that would be our answer, which corresponds with C, I believe, right? What else? On 27, we got another summation here. So let's check it out. We got so ultimately here what we're looking for is the sum of this series. Right. So if we look at our the way we have it arranged here, I guess, if you will, is if we were to put in some values here. Let's see what kind of things we'd get here for elements. If we put in a 0 here, we'd get 1 and 1 and 1. We'd ultimately get 1. If we put a 1 in here, we would get negative 1. We would get here, we'd get pi squared. So it'd be negative pi squared over a 1 in here would give us 2 factorial, which is 2. And then if we put a 2 in there, we'd get plus, because this would be plus 2 in there would be pi to the 4th. If I put a 4 in here, or excuse me, a 2 in here, I get 4 factorial. 4 factorial is, what, 24? And one more we'll do, let's say 3 gives us a negative. 3 in here would be pi to the 6th. 3 in here would give us 6 factorial, which 6 factorial would be 720. So the few terms that we have listed here would have been, I guess what would be convenient here is if it were something geometric, but is it in fact geometric? Ultimately, is there a common ratio between the bottom here? I mean, the top clearly is multiplied by pi squared each time, which is almost geometric. But the problem is we have this factorial down here. So if the factorial is down here, we multiply by 12, and multiply by 12 again, that doesn't give us 720. And this would be times 2, and then times 12, and so on. So ultimately, if there's no common ratio here, then it's not geometric. So I guess the next question is, what do we do with that then? Any ideas? And I guess keep in mind that that the values that we get here, there's no option for divergence here. We might be able to say, you might say, well, what if we tried the ratio test and see if it even converges? Well, all the options are converge here, so we don't need to waste any time doing that because we know it's going to have to converge. Let's think about this. And keep in mind things that we might know about an alternating series here. If I were to take this 1 here, keeping in mind that's the starting value, and I subtract this, okay, keeping in mind that this is going to be, say, let's just say for argument's sake that pi is just 3, because it could be anything here. So then we'd have 9 halves. So it'd be 1 minus 9 halves would be at negative 3 halves, right? And then if we did this one, keep in mind, and I'm going to make a little running total here. We're at 1, and then if we subtracted this element, again, this would be 9 over 2. So 9 over 2 would be 4.5. So it would be at negative 3.5 would be our running total. Okay, after 2 elements, we'd be at that. After 3 elements, we'd have, and again, I said just let this be 3. We'd have 81 over 24, which is going to be plus how much? So think about 81 over 24. It's going to be 3 and some change. True. So 3 would be 72. And then 9/24, if you will. And ultimately, that would get us up to pretty close to what? Again, I got 1 here. I got 9 here. 9 over 2. Again, 4.5. So we're at negative 3.5. And if we had 81 over 24, again, this would be 3. Would give us 72. 3 and 9/24. And ultimately, that would get us to negative 3.5. With that added, would be fairly close to 0. It would be negative something though. And then what's going to happen if I do this one? Ultimately, I'm going to go back to negative, aren't I? Okay. Keep in mind that when I added this one, it didn't get me back to positive, did it? Okay. And if I subtract that one, it's going to make it even more negative. Okay. And then if I add something else that's even smaller than this, it's going to get me up a little bit, but still in the what? Still in the negatives, right? And then the next one I'm going to subtract, I'm going to get even more negative, okay? And then ultimately, I'm going to just continue that same pattern. So again, just say for argument's sake that this was negative 1/2, okay? And I go down another something, let's say negative 3/4 or something, and then I come up a little bit to negative, let's say 5, 6, and then I go down a little bit further to, like, say negative 7/8 or something like that. Then ultimately, what are these steering towards? These are continuing to get a little bit smaller. And then again, just based on the fact that once we add this is the very biggest one that we're ever going to add. Everything that we add from here on out is going to be smaller than that. True. So if we added the biggest one we get and we got something still negative, we make it more negative, add a little bit back, make it more negative, add a little bit back, make it more negative, add a little more back. Okay, what's our only choice here on the list? Yeah, the -1. Okay. So again, what would have been convenient is if this had been geometric, then we could just use our a over 1 minus r formula. Right? Otherwise, we have to do a little bit of thinking about what that would be like in terms of a sequence that's alternating like that. Okay? And really, we can rule out anything but the -1 out of that. What else? On 28, we got a, and keep in mind that's a BC problem. Infinite series. 28, we have a differential equation. So remember the way we solve differential equations is we separate variables. Separate variables and then integrate. So we get y squared equals x squared plus c. And remember, we're going to put that c in immediately. So if we put in a 4, we'd get 16 here, 9 here. So that'll give me 7 equals c. So that means I'd have y squared equals x squared plus 7. And ultimately, I guess that's it. Just to make sure we got the right form here, though, I guess it would be is there a y squared minus x squared option? I guess that would be a, wouldn't it? You could bring the -7 over here and bring the y squared over here. So that would be an AB problem, just a separable differential equation. Alright, anything else on the sample exam 5 non-calculator part?